Yurong Lai. Yurong did his MD in medicine from Fujian University in China, and then went on to do a PhD in toxicology from Sapporo University in Japan. After a couple of postdoctoral research experience in Japan and in the University of Washington, he joined the pharma industry. And in pharma industry, he has worked with Pfizer, Bristol Myers Squibb, and now he is the senior director of drug metabolism at Gilead. He also is a fellow of the AAPS and adjunct faculty in the College of Pharmacy, University of Rhode Island. His current research projects involve absolute differences in hepatobiliary transporters across species, structure-activity relationship, and evaluation of in vitro in vivo models to predict human PK and toxicity. Today, Yurong will talk to us about the protein effect on the hepatic uptake and improvement of IVIVE in the PBPK model. Over to you, Yurong.
Thanks, Prakash. Can you hear me?
Yes, we can.
Okay, great. So let me share my desktop. Okay, how's my presentation goes?
It looks good, Yurong. You can go ahead.
Oh, okay, great. So yeah, thanks for introduction, and thanks for the organizers and Tangans and all to invite me to give this talk. So as introduced, my talk today is the protein effect on the hepatic uptake and how the improvements of IVIVE in a PBPK model. So I will start bring up to speed here. Here's what's in vitro to in vivo extrapolation, a so-called IVIVE of hepatic transporter medical clearance. So as a drug hunter, like PK scientist, it's very important part is to understand the efficacious exposure. In order to, there's a couple key determinant has to be figured out. So first is your bioavailability when you dose orally, and your how drugs are being cleared, and the half-life it is. So this clearance and the dose frequency is determined by this half-life. So then your half-life, drug half-life is determined by your volume distribution and the clearance. So now if we need to understand this, your efficacious exposure, you must know in the volume distribution and your clearance values. So before I go into the hepatic transporter, the IVIVE, let's review what's the IVIVE we have so far. I must bring this to my Pfizer colleague at the early days. Is my actually also my mentor as well during my Pfizer career. So Scott Buck. So these two publications actually bring up to the speed how we can use in vitro liver delivered reagents to understand in vivo human clearance numbers. So typically this use this equation. Basically, you incubate in vitro, understand what your drug in your microsome or hepatocyte, the half-life it is, and then normalizing use the hepatic the liver weight and your microsomal protein and also your incubation volumes and also your how much your microsomal being adding in the system. You get the in vitro intrinsic clearance, then you use this the first in publication described is the clearance plasma is normalized and unbound with the intrinsic clearance you obtained from in vitro. So later, this publication further to normalizing with unbound blood and also in vitro unbound microsomal binding. So this is the basis of the IVIVC for drugs that are cleared by hepatic metabolism enzymes. So quickly, this is Dr. Sciamma's investigation. We know that limitations because this is actually what Dr. Sciamma investigate. There is a rate determining processes. Actually, is a hepatic uptake, not metabolic. So what he investigates is use the few OATP substrates the lipid lowering starting drugs. And what he did here is that they used the clearance metabolic determine use the human unret driven microsome. So here, this is what I get with the clearance. So this then this across dots here is the use the hepatic hepatocyte uptake numbers. So you can see clearly if you use the clearance metabolic obtained from the human unret driven microsomes and largely underestimate your the in vivo observed clearance. So then identified that hepatic uptake is likely is a rate limiting or rate determining processes. So let's review how this uptake, the hepatic uptake can be the contribute to your the clearance processes. So this is actually nice cartoon from Eamon and Vorma and my Pfizer friends, and also we are working together with the same lab before. So here's the cartoon here. So the uptake transporter are expressed on the sinusoidal membrane of hepatocytes, and this they taking up your drug from blood to the liver. And in the general, if a compound is has a highly permeable compound, you can quickly go back to your bloodstream. But if your permeability is poor, your direction is to go in and less go in out. Then coming to your liver, it's actually is serve as a reservoir of the drug. So what you see from your PK curves, this is the standard textbook what we describe. Your compound dose IV have a very quick slight fast decay and then follow a slow elimination phase. So this is we call the distribution to the tissue. And when you dose orally, actually follow the absorption phase and then go to the elimination phase. This is textbook. But if your hepatic uptake is involved in your clearance mechanism, you will see that your fast decay is very deep and getting the slow of the elimination curve. So this distribution phase actually contribute not just from the tissue distribution, also hepatic uptake contributes to this first phase. We call alpha phase here. So technically, actually, you can see from this curve, your hepatic uptake is contribute only distribution, not elimination. So your elimination, in that case, still is driving by your metabolic or biliary clearance in this case. So let's look at how we can describe this clearance. Then, because this transporter are involved, then you have an uptake clearance and in your overall clearance mechanism. So in 1997, and Shiliani and Sandy Pan, so firstly introduced we call extended clearance concept to incorporate the processes of hepatic uptake, passive diffusion, and metabolism. So this is the fundamental basis equation. So from this equation, actually, there has a, quickly, there's a, understandable when your permeability is poor, your compounds, your determine actually is the your from this equation, your permeability, the passive permeability is poor. You cancel out basically is your metabolic clearance from this equation, because your metabolic clearance is way larger than your passive diffusion. This passive diffusion is a lot. Actually, you cancel out your clearance, metabolics and clearance. So your overall clearance is actually determined by your uptake into the liver. So this equation quickly being adapted in both academia and the pharmaceutical industry, and further delivered to a two drug classification systems. So one is from Pfizer colleagues. They have this Walmart, and we just listened his talk here. So they call standard clearance classification system, ECCS. The other one is called ECCS. In this, there's a triple C in the middle. So called Standard Clearance Concept Classification System, described by Novartis colleagues. So the ECC becomes a powerful tool to estimate the rate determining steps. So we already hear Walmart talking about this, classification system, 1A, 1B, right? So that's I'm not expanded too much time here, but is a very powerful tool. However, this equation does have limitations, because at that steady state, your uptake is equal to passive liver to blood, and to the passive blood to liver is almost zero. So because at a 10-0, right? So your uptake is only one direction going in, and passive also going in. But once your liver concentration is higher than your blood, your direction only one way, because your passive diffusion is a concentration gradient driver. So your passive diffusion only getting out, not getting in. So that's a steady state. Your uptake is equal to your passive to is uptake is equal to out. So in and equal to out. So getting the steady state. So that comes to give to you is this equation. They actually from here, this equation is a lack of the time dependency. So you don't have the time to at a time beginning a steady state situation. So at steady state, actually, you are getting in your passive is zero. So you only have a getting out here. But this, you putting this equation actually fix these numbers. So the end up your equations oversimplify these processes. So from here, sorry. So sorry, I don't know how this should be have some cartoon here. So basically, you simplify this processes is that you use this as your clearance numbers to convert your biphasic to a monophasic. Then your AUC, what you hear, your monophase AUC is equal to your biphasic AUC. However, your half-life is much shorter than your this biphasic AUC. So this is your outcome coming here. So we recently actually, Xiaoming and myself is we putting on this review article into the opinion on drug metabolism and toxicology, this journal. So we're talking about, so that basically your area AUC is predict well. you use this conversion to biphasic to a monophasic. So your AUC actually is this AUC is equal, is 2. However, when you look at the DDI outcomes, is different. With the transporter DDI, actually, you're changing the AUC, but you're not changing the half-life. But if you use the monophasic, you're changing the AUC, you do changing the half-life here. So that's why we see all the papers when they predict the clearance numbers, actually is ballpark is, numerically actually is good value, actually there's a good agreement with your observed changes. However, always they have half-life changes. You didn't catch up. So that's mean you were missing with the tail. Usually when you predict the transporter DDI versus the enzyme DDIs. So that's the coming to here. So then next question coming to here. So can we changing now we're focusing on the clearance predictions. Then to move on to the PK predictions, it's more like a focus on the profile now. So it's more like an advancement from the clearance prediction going to the PK prediction. So let's come into this early days, actually also from Dr. Stigma, from 2008, this paper. So he firstly used this PBPK modeling actually at a time, so construct this PBPK models, and basically this PBPK models consist of this compartment with the active uptake and passive diffusion on the semicellular membrane and the media clearance on the canalicular membrane on the liver. This is basically that it's the follow the cartoon I presented previously. And he also divided this liver as a 5 units with the 5 liver units in order to catch up this the curve. Basically, it's a mimic with the dispersion liver model. So they also constructed in this the organs, virtual organs, they construct a rapid content rapid equivalent compartment, and also the peripheral organ, actually like a muscle or kidney. So in this PBPK model at the time, still the constructor used this overall ECCS equation and to figure out this the clearance. You connect with the clearance, and also the 5 numbers actually is with this n is a 5 divided by 5 liver units. Then Lex is a physically at the time. I also involved here, and you can see the Hannah Jones and Hugh Barton is a very good modeler at the time we are working with. So we started to using adapted what the Dr. Stigma's the PBPK model also used the 5 unit of the liver. We constructed a PK model, use of 15 compartments. Basically, it's a virtual construct. Is also increase the virtual organ, and the most different from what Stigma used is that this we connected these organs use a mass balance differential equations rather than the kinetics clearance kinetics. So use a mass balance. So use the mass balance. You can see this time in this equation we're putting here. So have the time component into each organ. So this PK model also constructed 5 unit of liver, and with the kidney also is as an emulation organ. So you can see there's a clearance has into the here the is also emulation organ. So also we have a distribution organ as well. So we working on about seven the literature compounds here. So then use the in vitro the parameters obtained from the sandwich culture haplocyte. So then we use the model to fitting and simulation. We putting these two together. We identify there's the large scaling factor needed to in order to pushing your model to reasonably fit your human PK data. So the scaling factor actually is average geo means of about 60. So it's a 12 to even 161. It's huge scaling factors needed in order to predict right for the human PK. So there's two concerns here. Maybe while your PBPK model is constructed is more oversimplified processes of you putting the wrong assumptions. The other one, of course, is the uncertainty of the variations of the in vitro system, right? So your in vitro system not right. So we also use that scaling factor and the pro as an unbound fraction, and with the scaling factor, you can see the scaling factor need higher when your unbound fraction is low. So that means your highly bound compound, you need a more scaling factor. So then I moved to BMS. We further bring this to as our question. We also working on the not just OATP substrate, we also incorporate with OCP substrates. So we putting on the receiver study in both Santian and also metformin. So and at the time with those IV, we trying to getting the avoid the GI. Also we be able to, because the monkey will be getting the monkey liver concentration as well. So this model further being constructed, simultaneously can be able to not just the PK profile, also we have the liver concentration be simultaneously be able to fit together. So we still identify that the uptake scaling factor is needed. For example, the Zua study is about 7. So the Bosantan is 28, and then the metformin is the lowest, only 1.5. So we're also putting this unbound fraction and scaling factors. You see that's some trend to, because only 3 compounds here, but you do see the trend of this unbound fraction is correlated your scaling factor needed for the uptake clearance. So then we first think is, okay, your in vitro model may have exaggerate your transport expression. So then we look into what the suspension haplocyte and 6-hour short time period and also long-term 4 days culture of the sandwich culture, the monkey haplocytes. So coming to here, we think the 6-hour period actually is almost identical with the suspension. So short-term period actually didn't change. But sandwich culture monkey haplocyte, you can see OATP1B1 is reduced about half, and the PGP expression is almost 7-fold of suspension. So that's great. The changes of this after your 4 days culture. So then we do the analysis from here. So we actually do the sensitive analysis bridge models to here. First, we scared in vitro model parameters, right? This is without consider any. So we need about 10x of the scaling factor for the KPUU, that's liver concentration. So then we working with the correct with the transporter expression, we didn't see they much improvement. Actually, reduce a little bit, go 10 to go to 8. Interestingly, we see the active uptake was not limited by binding. If we think it is a binding concern, we can drop down this 10 to a 1.1, the scaling factor. If we consider this binding issues coming in, the scaling factors dropping down significantly. So then the question coming to is, what's the protein effect on hepatic uptake? That's coming to the main topic today here. This topic actually bring up to not now, actually, is, many 20, 30 years ago, actually, this review article, you can see, people already bothered for over 30 years at a time. So we always thinking, bilirubin is highly bound to your protein, but this is really efficient and being uptake to the liver and being eliminated from bile. That's a bilirubin. Similar with the fatty acid as well. So this coming to that's people starting to thinking, what is the protein effect on this hepatic uptake? The highly bound compounds will also be efficiently be eliminated here. So there's many papers come here. Then a few, Dr. Sujiyama Lens here. We have Pfizer Korea Walmart's paper and gene attack and Les Bennett. So people are very hot topic. I bring up one example that Dr. Sujiyama stated. So what he did is, increasing the protein in the system, and they see that overall the pitava starting uptake is going down with the protein increase, right? But if you normalizing with unbound fraction, actually your uptake clearance is going up. So you're normalizing with binding, so going up. So that comes to there's many mechanisms coming to why this happened, right? So why this protein acting in your in vitro system, you're normalizing with the unbound clearance going up. So there's a couple proposed mechanism coming to is it can be a facilitated uptake. So because it come your albumin being uptake by hepatocyte, then you're bringing your compound to the membrane and then being uptake into the. So there's also facilitate dissociation and also dissociation limiting and also diffusion limiting. So different mechanisms. Even recent ISIQ workshop is on April from Josh Unakat, what his lab coming to even what he's saying is likely is artificial effect. It's not any mechanism associated. Nevertheless, our lab is also in Gilead is really interesting with what's the protein binding will affect us coming to. So we conduct the in vitro hepatocyte uptake in human and monkey. Or we want to, we conduct, it's a large number. We use 15 OATP substrates. We're getting the unbound intrinsic uptake without the albumin in the system. So we also look at the difference in human and monkey hepatocyte uptake. And further, we checking with the IVVIVC in a PBPK modeling to see what this protein effect on uptake will improve in your PBPK models. So this is a very busy table by summarizing what this table talking about. So we got this unbound intrinsic active uptake clearance and using the system with a 10% serum, well, human hepatocyte with a human serum and monkey hepatocyte with a monkey serum. And then we compare with the result as the human serum. We see that there is a shift. Range is huge for 1.5 to 900 or 1.5 to close 800 in human or monkey. So this the higher fold difference some correlate with the highest protein binding compounds. So for example, the sorafenib, actually this is really high numbers to bring up to 900 something, 800. So this is typical. we cannot measure this protein binding. Actually, so, in the monkeys, we have to dilute our serum to not just be able to work in this protein binding is really super high with this number. So also you can see that the fold difference is highest in this table. So we also look at use this IVVIVC. Look at the scaling factor. For this compounds, we compare with the Hannah Jones what their scaling factor needed, and then we use this 10% serum in the hepatocyte uptake. You can see that dramatically reduced here. Interestingly, actually, we also did 3 compounds from this human list in monkey. So we get it. So you can see the 3 compounds, 7.2 for the human and 10 for monkey, and 4.0 for this and 4.5 for the monkey, and the 4.8 is 7.1. So this coming to the very close scaling factor used to human and a monkey. Then the question coming to us, can we use the monkey PBPK model to prospective human PK prediction? This is very interesting for the drug discovery phase, because at the time we don't have a human PK. We need to predict human PK, right? So not just predict human clearance. Now we need to predict human PK profile, what it looks like. So the some thought from that table coming in is that we can develop the PBPK model in monkey and validate it. The outcome of this monkey validation is just scaling factor. Then we use the same setting of the in vitro assay, exactly same with the monkey. Only difference, the human hepatocyte uptake use human serum, and monkey use the monkey protein. So then getting the scaling factor we to predict human. So we're starting to exercise with this chart here. So we first we look at the 3 compounds in monkey here. So then this 3 actually is a good OATP substrate. We do the IV infusion in monkey. We do the curve fitting and develop and getting scaling factors. The scaling factors are for the Veratagras and the Pitava study and the SUA study. So then when we do this fitting, very interestingly also, your fitting, you can depends what parameters you putting in and initial numbers. You can have all the scenario here. You can get a good fit. Basically, this is more like a matching. You can matching very well, not a modeling, right? So you can see that scenario 1, fitting 1 is a uptake driving, but 4 is the metabolic driving. I think my time is here. I have a few slides already down here. So then bring up to, we need to validate this fitting. So then we need to simultaneously, fitting with the liver concentration. Then you'll be able to figure out which one scenario is the right scenario. So this is a model validation. We use the major liver concentration. In monkey, we fix that. So then we believe this is the scaling factor is validated. Now the exactly use the monkey scaling factor, but use the human in vitro numbers with the human hepatocyte with the human serum in the incubation. This prediction actually is a prospective. Then overlay with what a human PK. You see how good this prediction are. So we're missing the tail with the Lusova study. We end up, we need to get in the 10 to 15% of the enterohepatic recirculation. Then we can catch up the tail. But even lost this tail, the prediction is quite good, because this tail actually the AUC contribution is not much. So this is coming to give us the very important finding, because we'll be able to proactively, this is proactively, not the fitting. So this is coming to, this is simulated numbers, and the monkeys, this, you can see this SF is exactly same from here for the different parameters. So then you be able to predict human is proactively, so prospectively. So then we propose this framework here now. So we can use the probe animal, right? Use the in vitro and build this PBPK model. And once your PBPK model been validated, so we use the major liver concentration or use a DDI, if you know that's your subject. Then we're getting the scaling factor. Then we build the human PBPK model. So importantly, this in vitro assay has to be exactly the same, use the monkey and the human. Only difference is the monkey with a monkey serum, human with a human serum. Then you initial model, your model could be able to further refining once your human PK available. Then you would this PK model be able to predict your DDIs, your special preparations, your PPK, PD, whatever you want to for further use these models. So this is currently we're going to pursuing this our current general practice. So summary here is that this last question. So we're adding this species-specific serum protein into this the in vitro system. Actually, we'll be able to getting this cancel out this the species-specific variabilities. So we see the reduction of this empirical scaling factors. So currently the scaling factor is 3 to 7, so largely reduced from 100, so coming to. So of course when you getting the animal the validation, you need to use the major organ concentration or DDI data to getting the reliable scaling factor, because I showed you that if you put in initial numbers, initial inputs differently, you're getting totally different scenario outcomes. You have to validate, moving from the matching to a modeling. Actually, that's the very important part. So in vitro parameters are very important. Of course, that you're adding a protein, you need to validate 10%, 5%. We actually 10% is currently our condition to use. So we still don't know why this coming to different proposed, or even somebody saying that this artificial effect, whatever that, still we don't know yet. There's a knowledge gap for sure. So we need that getting to understanding. So over years, as the introductions at the beginning, so I moving from Pfizer to BMS and to Gilead now. So many people are involved in this work. Actually, in the early days, Hannah Jones, Volma, Amon, and Bridge and Xiaoming, and doing quite a lot, understanding the scaling factors and translational modeling. Thank you.
Thanks a lot, Yurong, for a very interesting talk. So we do have a few questions that are coming up. So first question, Varma, you want to ask it yourself?
Hey, Yurong, can you hear me?
Yeah.
Yes.
Yeah, I'm just interested in your thoughts on the albumin effect. I don't know if you're seeing my question there. What do you think about albumin reducing non-specific binding in the in vitro uptake studies? Because you only see this effect for highly bound drugs, right? Is this that dials up into what Josh is implying about an artifact versus a real albumin-mediated uptake effect?
Well, I not fully agree what the Josh's theory, artificial effect, because that apply to all. I do believe that constitute may have your affinity is basically a binding affinity with the transporter affinity, right? So I would think that microenvironment, your free fraction maybe go up. When typically for the highly bound compounds, because you keep, this is like a sink effect. So what my thinking here is a thinking effect, because your transporter continue bring your free fraction up to the liver. So then you will continue release from your binding site. So end up your free fraction is not your major. That environment, your free fractions increase. So I would think more like a sink effect coming to. It's not just the artificial. But I don't have evidence now. So for this thing.
Okay, thanks.
Yeah. The next question is from Vamshi. Vamshi, you want to ask, or do you want me to go ahead and ask the question?
Take that one. So hi Rang. I have two questions. I want to know what is your viability when hepatocytes were supplemented with the sera?
Yes.
And how relevant is the clinical situation?
That's a good question. So yes, you need a very well trained the scientist. So with our scientists being trained for the control over years, so we can go into the CV percentage, the project control, right? So typical use of Pitava study and the SUA study. So the variations are typically lower 20%, and maximum is 30% is our cutoffs. So we internally, if we greater than 30%, we'll reject the data. So if you look at the paper, we use also different lots. That's agreements very good. Actually, that you see even the different lots, the variations really not that much. Yeah.
So and how much this is relevant to the clinical situation when we use the sera and compared to the plasma? Plasma has everything in it. You also see the non-specific binding to the plasma for some of the compounds. But when you use the sera, and that will be an artificial situation, how does that correlate to the clinical relevance?
Yeah, we use the plasma and also use the serum and use the albumin, right, to try different conditions. Yeah. I think I personally I would like to use the plasma. I do agree what you're saying here, that plasma and the contents are slightly different from the serum. But technically, because we use the oil spin, so when you putting on the plasma, sometimes it can forming like a gel-like. It's not easy to spin on down your hepatocytes. So end up in the middle, we feel there's more comparable with the 10% of the serum, the best results so far we're getting. So technically and also considering data and so on. So I do agree that maybe 100% plasma would be best, but technically we cannot do this. Yeah.
Okay. Those are my two questions.
Okay.
Thank you, Yurang.
Thanks, Vamshi. Thanks, Yurang. And there's one more. I think we are almost out of time. There's one more question from Vinay. I know Vinay is online. If he wants to ask it, okay, I'll go ahead and ask it for on behalf of Vinay. Okay, doesn't look like Vinay is. He could have. So anyway, the question is about relating to